Hello, everybody. My name is Emily June, and I'm an assistant professor at Boston University. So greetings from Boston. Today, I'm going to talk about some of the work I've been doing over the past year or so on creating and disseminating benchmark datasets of mechanical simulation results, specifically two datasets, Mechanical MNIST and BIC. And I'll keep the presentation short, but please don't hesitate to get in touch with me at any point to discuss further. So super briefly, why would we want to create metamodels or models of models? The answer to that is that metamodels are useful primarily when full fidelity simulations are too computationally expensive to accomplish our goals. For example, a single simulation might take hours or days to run, and we might need several thousands of simulations to fully explore the input parameter space. And we can run a bank of full fidelity simulations and then use machine learning approaches to create metamodels that make accurate predictions about simulation results given previously unseen parameters with a trivial amount of computational time. And this has been a really popular topic recently in the literature. There are just a few examples of this on the slide. And it's been having methodological applications in multi-scale modeling, optimization, uncertainty quantification, real-time prediction, data integration, and more. However, despite all of this recent work, there isn't a clear picture of what types or architectures of metamodels will work best on engineering mechanics relevant data. So one potential way to overcome this is to look at other fields, specifically computer vision, where benchmark datasets have had a massive impact in demonstrating the efficacy of new methods and motivating research. Two of the most popular examples are shown here. So we have ImageNet, a collection of labeled images, and MNIST, a collection of labeled handwritten digits. And notably, the barrier to entry for working with these datasets is super low. As shown here, you can download MNIST in 2 lines of code. Probably there's a way to download it in 1 line of code. And these datasets make it easy to compare different machine learning models through their benchmark performance. So in this talk, I'm going to show my early attempts at creating something similar for the mechanics community. Specifically, I'm going to introduce 2 benchmark datasets that I created and provide a snapshot of what I've done with them so far. And I sincerely hope that you'll be inspired to check them out. So the first one is the buckling instability classification dataset, and it's a dataset for classification problems in mechanics. And the second is Mechanical MNIST, a dataset for regression problems in mechanics. And you can download them by following the links here or attaching to these QR codes. And I'll also try and post the links where I upload this video. So just a little bit more detail. In the first dataset, BIC, we have a column with heterogeneous material properties subject to a fixed level of applied displacement, slightly larger than the Euler buckling load if it were a homogeneous column. And then using eigenvalue analysis, we classify it as either stable or unstable. And in the BIC1 dataset, there are 2 potential moduli and all combinations are simulated. In the BIC2 dataset, there are 3 potential moduli, and we do 100,000 combinations. And in the BIC3 dataset, there is a continuous distribution of moduli, and we do 100,000 combinations of simulations as well. And we conduct all simulations using the open source finite element library Phoenix with PETSI and SLEPSI. And you can also take a look at all of our code on GitHub. And as you can see from these examples, it's not necessarily obvious to the human eye which patterns will be stable and which patterns will be unstable, but not necessarily surprisingly, we can create a meta model using machine learning to classify each column as either stable or unstable, and the performance is quite good. So with just 1,000 simulation results for training, support vector machines, neural networks, and Gaussian process classification all perform quite well. Gaussian process classification performs the best with an AUC of 0.986 on the test data from just 1,000 training points. And you can see this corresponds to nearly perfect classification. And as we add more training points, the performance also continues to improve. However, just as kind of a little snapshot of some of what we've explored with this data set, we can also break the meta model that we showed on the previous slide. So specifically with access to additional training data, we can create an attack model where a neural network is trained to specifically fool the Gaussian process classification meta model. And we can show that with additional training data available to the adversarial actor, it's possible to fool the original meta model in predicting that ground truth unstable structures will be stable. And I like this example because it essentially shows a current limitation of the real world use of metamodels, essentially that they're vulnerable to adversarial attacks, and a clear need for methods that can make these models more robust. Okay, so changing gears a little bit, I'm now going to introduce our second benchmark dataset, Mechanical MNIST. In this dataset, we're directly inspired by the original MNIST dataset of handwritten digits. And we're kind of inspired by this original MNIST dataset because it's well known, but also because it's a really nice size. It's small enough to download on any modern computer with a standard Wi-Fi connection, but then also large enough to meaningfully train neural networks, especially convolutional neural networks. So here we convert the 70,000 images in MNIST to 70,000 simulations of a neo-Hookean material with varying modulus, where the digit is a high modulus material embedded in a low modulus matrix. And then for each 28 by 28 input bitmap, we report full field displacements, total change in strain energy, and total reaction force at multiple steps of applied displacement. And again, we conduct all simulations with the open source library Phoenix, and our code is freely available on GitHub if you're interested. So the Mechanical MNIST dataset contains multiple different load cases and also multiple different simulation fidelity levels. So here we show two example load cases, uniaxial extension and equibiaxial extension. And we also show full fidelity simulation, so a fully refined mesh with quadratic elements, and then also low fidelity simulations where we have an unrefined mesh with linear elements and varying degrees of coarseness, in some cases coarser than the 28 by 28 pattern. And we also show low fidelity simulations where we just apply a tiny displacement perturbation rather than the full 50% extension shown in the other simulations. And just again, kind of as a snapshot of what we've been working on with this data set, here I show an example of using transfer learning where we leverage the knowledge gained while solving one problem to solving a different but related problem to take advantage of low fidelity simulation results to make high fidelity predictions with fewer high fidelity simulations required. So if you consider just the data point that's circled in blue on this slide, for that point, we pre-train a convolutional neural network with 60,000 low fidelity simulations and then fine tune it with 100 high fidelity simulation results. And we end up with a metamodel that has a comparable test error to a metamodel trained with 60,000 high fidelity simulations. And in this plot, we kind of show a summary of these results. And you can see that we have mean absolute percent test error on the y-axis and the number of high fidelity training samples on the x-axis. And then each curve corresponds to the number of low fidelity simulations used for pre-training. So in the black curve, no simulations are used for pre-training and the performance is worse. And really, as you can see, perhaps not surprisingly, pre-training on the low fidelity data leads to a substantial improvement in model performance. And these results are interesting because they nicely show the potential of a very simple method of transfer learning for creating better quality metamodels from less expensive training data, which you can imagine will be much more important as you move to simulations conducted in 3D that really take days to run. So in conclusion, we've created two benchmark data sets relevant to mechanical problems. And if you follow the links or QR codes on the slide, you can download them and use them to test your own methods and potentially surpass the baseline performance that I report in these papers or take on new problems. And again, please don't hesitate to get in touch with me if you have questions or comments about this work. I sincerely hope that it's useful to the broader research community. And thank you very much for listening to my talk and have a nice conference. Bye.